Hey everyone. So the last thing we're going to talk about in DSC 10 is prediction. This is kind of a machine learning topic. I want to predict the future or predict something that I don't know based on data that I currently have. We're going to do this with a technique called regression, and regression is a big topic in statistics, so you might have heard of it before, you might have even seen regression previously. We're going to approach it with a slightly different angle. So let's talk about prediction. In prediction, my goal is to predict something that I don't know or something that has yet to happen using data that I gathered from the past. So for instance, I might want to predict the height of a child given the height of their parents, or given my age, what is my risk of heart disease? In each of these questions, there are two characteristics. One of them is known, one of them is unknown. So for instance, I know the height of the parents, I don't know what the height of the child will be. Or I know my age, I don't know my risk of heart disease. So the way that we kind of figure out the answer to these questions in a statistical sense is we use data. And this makes a lot of sense because if I say I am 60 years old versus 30 years old, you probably could guess that at 60 years old you have a higher risk of heart disease than you do when you're 30. How do we know that? Well, we've seen it. We've seen it in the data. We kind of know that historically this has been the trend. And so this is exactly what we'll do when we're trying to make predictions. We will somehow comb through a bunch of historical data, try to find a trend, and then use that trend to make a prediction. So to make a prediction, I need there to be a trend. And we used a word at the beginning of the quarter that was kind of synonymous with trend, and that word was association. So let's go back to a data set that we've seen before. This is a data set of parent heights versus the height of their children. So remember, the mid-parent height is kind of like an average of the height of the father and the mother. And then we have, for every child, we have the height of their parents, their average height, their average mid-parent height. So we can plot a scatter plot just like this. We see that there is a sort of trend here, that the taller the parents are, the taller their children tend to be. So each dot here is a child. We have their height and we have their mid-parents' height. And we see that there is sort of an association here. There is a trend. And we're going to be able to use this trend to predict, given a particular mid-parent height, what the child height will be. Of course, we can't predict it exactly, but we might get close. So what we did before is we did this kind of very intuitive but very computational approach, where what we did is we said, okay, if I want to predict the height of a child whose parents are 72 inches tall in terms of mid-parent height, what I'll do is I will find all of the children whose parents are close to 72 inches tall in mid-parent height, and I'll just average their height, and I'll get something that's kind of like in the middle here. And we wrote this function back in the middle of the quarter to do this. So I'm just going to do a query defined, given an input parent height, a mid-parent height, find every instance in the data set where the parent height is within 0.5 inches, and then I return the mean of the child heights within that subset of the data. So let's go ahead and run this. Remember, it takes a second because I'm going to do this for every child in the data set. I'm going to take this predict child function, which predicts the height of the child based on the mid-parent's height. I'm going to run that over the entire data set so I get back the predictions for every child. And this is what I get. So this is the gold line here, the line of gold dots. These are the predictions. And what we kind of observe, first of all, is that it's kind of a line. It's kind of like a straight line, and it's sloped upwards so that the higher the mid-parent height, the higher the prediction is. So what we've plotted here is what you might call the graph of averages. So for every x value, we grouped the data that was close to it and averaged their y values. So that yellow line is truly a graph of averages. So think back, we've talked about associations before at the beginning of the quarter. An association is any apparent relationship between two variables, such that when one is large, the other might be small, or the other might be large, or so and so forth. Basically, it looks like there's sort of a a trend. Okay, we've used the word positive and negative to describe these trends. A positive association is one where if X is large, then Y is large as well. So for instance, when the temperature goes up, the number of ice cream cones sold goes up. That's a positive association. Or when the mid-parent height increases, the child height increases. This is a positive association between these two variables. A negative association is basically the opposite, such that when one goes up, the other one goes down. So for instance, when the temperature goes up, the number of winter coats goes down. Number of winter coats sold goes down. Okay. Another word we've used is pattern. Pattern just means any discernible sort of shape to the data. We can have a linear pattern. That's what we saw here. It looks like a line, a straight line. Or we could have a nonlinear pattern, which looks like something other than a straight line, as we'll see in a second. So let's take a look at another data set. This is a data set of hybrid cars. So I have 153 hybrid cars, the year that the car came out, how much the car cost, some measure of the car's acceleration. The larger this number, the faster it can accelerate. Miles per gallon, so how efficient the car is. The larger this number, the more efficient it is. And then just what type of car is it? A compact car, a two-seater, and so forth. So what I want to do here is I want to take a look at several pairs of variables and look at their relationships. So for instance, acceleration and price. How are these two things related? Is there an association between these two variables? As acceleration increases, does price increase, and so forth? So we've plotted here a scatter plot, which is pretty much one of the main tools that we use to detect associations, scatter plots. And here's what we see. So as acceleration increases, it looks like the price of the car also tends to increase. And this kind of makes sense. If you think about cars which can accelerate very quickly, they tend to be sports cars or things like a Tesla. Those cost more, just on average, right? So it's not always the case. You can notice this car right here accelerates pretty quickly, but it's pretty cheap. It doesn't apply to every car in the data set, but in aggregate, you see this sort of trend. So now let's take a look at another pair of variables. Fuel economy, basically how efficient is that car, and price. Is there an association between these, and what kind of association? So before we plot the scatter plot, it's useful to kind of stop and think. What do you think will happen if I use fuel economy as the x-axis, and on the y-axis, the price? What do you expect to see? Well, so let's plot it and take a look. So it looks like as the car becomes more fuel efficient, the price actually decreases. Or to put it another way, cars which are not very fuel efficient are kind of expensive. That might have been the opposite of what you were thinking. Like if I think of a car that's really fuel efficient, maybe I think, wow, maybe it's expensive because you have to pay a lot to get that sort of technology that makes it very fuel efficient. But what is actually happening here? Why do we see this sort of trend? So it looks kind of like people are willing to pay less for certain cars because they want poor fuel economy. Is that the case? I'm not so sure. I think what's happening here is that cars with poor fuel economy are kind of like sports cars. They're the fancy cars that are expensive. And so it just so happens that cars with poor fuel economy are quite expensive because they are a sports car, a performance car. Now, another thing to note here is that this doesn't look linear. This trend doesn't look like it has a linear sort of pattern to it. I would say that this looks like a curve, a nonlinear pattern. In fact, if you kind of had to draw a line that describes this curve, it wouldn't be a straight line. It might be something like 1 over x, where x is miles per gallon. So it would be kind of like a curve like this. Now, this data that we have here, it's all in American units. So miles per gallon, price in US dollars. what if we want to convert this to kilometers, for instance? Well, we can go ahead and do that. This is some code that we've seen before. So I'm just going to take the miles per gallon column, multiply it by a conversion factor, and I'm going to convert it to kilometers per liter. For the price, I'm going to convert the MSRP in dollars, the price in dollars, to euros. And this is an old conversion factor, but you get the idea. Assign those back to our table and then plot a scatter plot. The key thing here is going to be that changing the scale in a linear way like this, just sort of like we call this a linear change in units, or just doing any sort of multiplication and then doing an adding and subtracting. But converting units like this, how's that going to change the plot that we see? So before we had price, miles per gallon, like this. I'm going to convert all of these numbers to price in euros. I'm going to convert all of these numbers to kilometers per liter. When I plot it, you'll notice I get exactly the same figure back. The only difference is the scale of the y-axis and the x-axis. So the takeaway from this slide is that a linear change in units doesn't change the shape of the plot, okay? But the scale does change, right? The scale of the x-axis, and the y-axis changes. Okay, so remember this is what we had before, MSRP in US dollars and miles per gallon. Flipping back and forth between the two, you see that they are exactly the same except for their axes.